In this section, we'll discuss semaphore. We can see semaphore as an extension to locks. A semaphore is an object that consists of a private counter, a private waiting set of threads, and method to acquire and release a semaphore. Basically, semaphore extend the concept of lock and represent another solution to the critical section problem. Well, semaphore answer to the requirement to enable access to a set of shared resources to a defined number of threads. Let's consider the example on the right-hand side of this slide. Basically, we have the semaphore, and the main difference with the lock is that the variable can represent the number of threads that can access the resource. So basically here it's just like having a lock that enables the access to two threads. So in the beginning, when the lock is open, the lock is set up to 2, which is the number of threads that are enabled to access the critical section. The thread T0 checks the lock and asks to access it. And as we can see now, the thread has entered the critical section. And the lock is 1. It is still open. As a consequence, when thread T1 approaches the critical section and checks the lock, it obtains a simple result. The lock is still open. So basically the thread can access into the critical section. Now, in the figure, we can see that both thread T0 and thread T1 have entered into the critical section. And now the lock is closed. When thread T2 approaches the critical section and checks the lock, checks the semaphore, basically it's not allowed to enter into the critical section. In particular, T2 cannot enter in the critical section until either T0 or T1 release their spot, release the semaphore. But one question arises. Why do we need semaphore in the first place? So far we define locks, and we explained that the access to critical section was expected to guarantee that a single thread was executing in the critical section. So why do we need to enable more than one thread entering the critical station in the critical section? The reason is simple. There are situations where we have a bounded number of resources that can be accessed by a limited number of threads. For this situation, semaphore provide the required mechanism that guarantees that only a defined number of threads can access the set of available resources. Now it's time to have our hands dirty and to understand how to implement semaphore in Python. As usual, we refer to the threading module, and in particular we have to consider the semaphore class. This class implements the semaphore object, and the semaphore object manages an atomic counter representing the number of threads that can execute in the critical section. By default, the number is set to 1, so the default behavior of the semaphore is the same as the lock. Similarly to lock and unlock, we have acquire and release method that makes it possible for a thread to acquire and to release a spot in a semaphore, so to enter the critical section. They have the same meaning, the same semantic they have in locks. So it's very similar. The only difference is that now more than one thread can enter the critical section. And another important thing is that you can use a slightly variation in release, so that you can increment the internal counter by a number defined by the programmer. So you can release more than one spot in the semaphore. That's something very simple. It's really a minor variation to what we have seen so far. Really often, we said it before, semaphore used to guard resources with limited capacity. So a slightly stronger semantic has been provided to this bounded semaphore. And the only difference with semaphore is that the bounded semaphore checks to make sure that its current value does not exceed its initial value. So the bounded semaphore may help you in guarantees that the number of threads that were expected to enter the critical section is never exceeded, and possibly this can help you spotting software bugs, software anomalies. Let me stress that in the case that the value of the semaphore exceeded the initial value, a value error exception is raised, so you can understand that a problem has occurred, and you can manage the problem. You can log it, and you can do what's needed to check your software and fix. Let's analyze a simple Python example where we can experiment semaphores. Well, let's start by considering the main function. So basically, we have a list T, and the list is used to manage 5 threads. So we create 5 threads, and we pass the myThread function that implements the thread logic to the target, and an argument. The argument is a number. So the first iteration we pass 0, sorry. Then we pass 1, 2, 3, 4, and then we run all the threads. So we run thread 0, thread 1, thread 2, thread 4. Finally, we wait for all threads to terminate their execution. As you can see, here we have a global variable, the semaphore, sem, and you can see that well, here we opted for a global variable. However, we could have passed the semaphore. You could have passed in the semaphore to the thread as a parameter. Would have been more correct. And however, the best solution is always to rely on object orientation to have clean and reusable code as usual. Then we have the myThread function. The myThread function takes a number as a parameter and makes use of the semaphore. Exactly like we did with thread, we use the with statement. So with semaphore, with sem, we print the name of the Fred number. We sleep for 1 second, and then the thread can terminate its execution. Now, one may wonder what's going to happen when we run this simple application. So basically, what we have is a semaphore. We create 5 threads. We start 5 threads. All the 5 threads arrive to the semaphore. And what is going to happen there? Let's see. Let's try to run this simple application. Well, let's try to understand what we have seen in this output. Well, we run the application from the command line as usual, and then we have thread 0 and 1 that enter into the critical section, while thread 2, 3, and 4 are blocked. So thread 0 and 1 can print their name and wait 1 second. Then they release the semaphore, and thread 2 and 3 can enter the critical section, can print their name, can wait for 1 second, and they can release the semaphore, so that thread 4 can now enter in the critical section, can print its name, and wait 1 second. Then thread 4 can release the semaphore, and then we have the main function waiting for all the threads to terminate. And thread 0 is terminated, thread 1 terminated, 2, 3, 4 is terminated. The application itself can terminate, and then we can exit. That's it, that's all. In this section, we discuss the semaphore model and its implementation. And we also discuss how to implement semaphores in Python. And we experimented semaphores in a simple demo.